We're going to look at the normal distribution. Now, mathematical models, attempt to characterize some aspects of reality. And again, not perfectly, but enough to provide useful information. And so the normal distribution, I'm going to abbreviate this just DIST. Oh, I'm not, I got enough room. I don't know why I thought it was less room. I think it was a little. Depicts an important aspect of reality. When it comes to distribution types, okay? For example, human height is thought to be, approximately, abbreviate this, normally distributed. Again, close enough to be considered normally distributed. Now, the truth is more complicated, so you must take into account categorizing factors such as gender, age, background, and other realities, right? So if you try to model adults and children, each one is a different normal distribution. Um, so together, it would be a little different. So think of them, it could even result in a bimodal. Uh, so think again of the model as a like starting point. It's not supposed to be perfect. Getting us close to reality. For example, what factors do you think contribute to the height of a person? Well, I mean, one thing comes to mind is nutrition, genetics, health, which is, part of it's a combination of things. Health of a person, maybe exercise or sleep. I'm sure you could think of other ones, but again, there's some factors that do contribute to the final outcome, how tall a person is. Okay. So here's what a normal model looks like. And you've seen this before. It looks like this. In fact, I want to make it a little longer because what I'm about to do. I want some space. But this is what sometimes you known as a bell curve. Okay. But it has a more appropriate type of normal distribution. And once in a while, you'll also see Gaussian curve or distribution. As a matter of fact, if you own, one of these more fancy cameras, I think it's for light distribution, you'll see a Gaussian curve all of a sudden. Not that I know exactly, but it has to do with the amount of light, but I have no idea beyond that. All right, so, and notice we're going to mark the horizontal axis in terms of standard deviations. Okay, so we're going to mark this horizontal axis in terms of standard deviations. And the axis itself, I'm going to just call this X, just like you did in algebra. But this is really, what this represents is your measurement. Okay, that's what this axis is. So it could be, if it's height, then X is the height of a person. If it's weight, then X is the weight of a person. And of course, we don't have to use X. We can use any variable we want. Now, the fact is the area under a normal curve is, what is it? 1 square unit. Okay. So that is the total area under this curve. And notice this curve never touches that axis. It's this axis here is an asymptote. So this goes like this forever, but the further I go on, the closer this will get to that line, but it'll never touch. So it forms, again, a horizontal axis. Horizontal asymptote. So the area, what does the area represent? Well, the area represents relative frequency. Probability, if you were, you know, we're thinking of it as in terms of probability theory, which we will. A proportion, some percentiles. Okay. Now, the reason for the area being 1 is that it represents 100% of the population. Okay. So again, remember, you cannot have more than 100%, less than 100%. And this curve is also part of something else, which I'll mention in a minute. I don't want to get ahead of myself. But like I said, I'm going to mark the horizontal in terms of standard deviations. So one thing we can do is this. So X represents the measurement. Well, first I'll do it 2 different ways. I'm going to mark the center here. And I'm going to use this symbol. And what is this symbol? This is going to be the mean, but not any mean. In fact, I'm going to write it right underneath here. This is going to be the population mean. I might as well introduce another symbol right now. So this is the Greek letter mu. It looks like a U with a fancy tail on it at the beginning. And this is the population mean. Again, this is symbols we're going to use all the time. We can also use another set of notation, function notation. Remember what function notation is in algebra? You had this symbol here when you used an algebra, and you had your input and you had your output, and the function is what caused the input to connect to the output. Okay. So we're going to use the same notation, but we're going to connect 2 different things. So what I want to know is the mean of this population, the center of it. So another notation we can use is this E, and then we'll say E of what? And what does E stand for? The E is for expected. I sometimes call it the expected value. And what is the expected value? Well, again, if you told like, let's talk about height. Suppose that all 5th graders are on average 60 inches tall. Then if I grabbed a random, let us say, 5th grader, and then say, well, how tall is that person? We go ahead and looking at him. Well, I would say I would expect that child to be around 50 inches tall. Well, did I say 50 inches or 60 inches? I think 60 inches. So in other words, I will quote the mean, and it's just a value you're expecting to get. It's not the one you're actually going to get, but it's kind of giving you a representative for all children. Okay. So we'll use this letter here, which is mu. So there's again population mean. So mu equals population mean, and it's pronounced mu. Okay, that is mu. Okay. Now I'm going to do something else. I said I was going to mark this. So I'm going to mark it. And you'll see where this curve starts to go down right here, somewhere right there. This distance right here is about 1 standard deviation. Okay. And I'm going to mark it using a population standard deviation, sigma. So again, what we have here is sigma equals population standard deviation. Okay, and that is 1 standard deviation. So really, what is this point right here? I'm going to mark it just below, just here, and this is mu plus sigma. If I go measure another sigma right here, the value now will be mu plus 2 sigma. So we're going to measure everything distance in terms of standard deviations. So if I go one more, I'm going to go mu plus 3 sigma. And of course, I can keep going, 4 sigma, 5 sigma, and so on. This has no ending. right? This goes out to positive infinity. And on the other side, this goes out to negative infinity. Oh, heads out. Again, it's never ending. So if, again, I went to the left, now this would be, again, marking somewhere right there. Approximate, this is mu minus sigma. Then again, going that length, approximately. Trying to get as precise as possible. This would be mu minus 2 sigma, and then this is mu minus 3 sigma, and so on, 4, and 5, and 6, and 7, or 8, or 9. What you want to notice is that the further we go out, the area underneath this gets smaller and smaller. And remember, what we want to present is the area. The whole purpose of this is to represent the area, okay? So I'm going to do something right over here. I'm going to come over down here now, and I'm going to create another axis, but I'm going to mark these. If I had a ruler, you would see this more direct, but I'm just eyeballing it here. These values, marks are just directly underneath each other. And what is it I'm about to do? Well, I'm about to create, change all these numbers to what is called z-scores. So, well, if I call x my measurement, then the z-score is this. The z-score is going to mark how many standard deviations I am away from the mean. So for example, mu here is 0 standard deviations because it is right at the center. It is 0 sigma away from the mean. And again, the formula to convert from this to this is the following. X, again, right now, again, this could be any variable, but I'm just using anything. So it's always going to be measure the distance away from the mean and divide by sigma. So for example, if I wanted to look at this value, I'm going to do it here at the top. So this value right here is, again, I'm going to just do it symbolically so you can see everything. So I'm going to go mu plus sigma. That's this distance here. That's that x. But I'm subtracting mu and dividing by 1 sigma, as I've shown here. So again, notice mu, sigma, mu, sigma. When I do this, what do I get? Well, mu minus mu is 0. 0 plus sigma is sigma. And what I have is sigma divided by sigma. This is 1. So this is 1 standard deviation. What about that one? If I did what I just did above, I would get 2 and 3. And if I kept going, 4 and so on. 5, 6, 7. On the other side, if I did this on the other side, I would get -1, -2, -3. Okay, so this is, we can talk about this curve in terms of the actual measurements, or we can talk about it in terms of its z-scores. Okay, so we're going to talk a lot of it on the z-scores. We want to get used to doing this. It's a way of letting the reader know how extreme this measurement is. So the model used to describe the distribution. So again, this model is used to describe the distribution of a continuous variable. Okay, so what that means is that it's not going to have any breaks at all. So if we go 1, 2, 3, 4, that's not continuous if I don't allow anything in between. But if I allow real numbers in between, then there's an infinity of values between 1 and 2. In other words, no matter how I slice this, there's going to always be an infinity of values, no matter how small I make it. Okay, because it's continuous. There's no gaps between the numbers. Okay, that's what that means. Now, this graph, the way I've drawn it, is a true distribution. And what the heck do I mean by true distribution? Well, the graph is just like a parameter. Parameter tells you exactly So we talked about parameters, but in terms of summaries, but we can also talk about it in terms of like a graph. This thing is perfect. Like this would be model if a height would actually look like this. This would model it perfectly. No, it's the exact thing. Um, so that's what this distribution sort of represents, the way I've drawn it. Um, so it's summarizing the entire population. If you sample data and create a histogram, for example, so you're sampling from, again, this says whatever this measurement, I'm sampling from it, but I create a histogram, then the histogram is like a statistic. So we usually just use these words for not graphs, only calculations. But the reality is that's what this is. Histogram is like a statistic because it's summarizing data from a sample. Okay, so this is perfect, a perfect representation of some distribution. Okay. So now let's look at the area under the normal curve. So right now we're trying to get to understand how this whole thing works. And again, notice I wrote this kind of cryptic thing, P of an event. And again, this is function notation. And the way this function notation is going to work is going to be this. You're going to write some statement, which we'll call an event. Okay? It's just some measurement or some description of something. This is just, it could be numerical, it could be a word, it could be anything. For us, we're just going to write down an interval that we're interested in. And the output of this is the probability. Okay, but again, notice the probability has all these other terminologies. It could be relative frequency, probability, proportion, percentile. Okay, so but that's the output we're looking for. So again, this is tied to function notation, where again we input something into the function, out comes out this output. So this is just a way of describing to the reader what we're about to do. So currently our goal is just to get comfortable with this distribution. It's central to the concept in the second half of this course. First, let's get familiar with, again, the area on a normal curve using a mnemonic. And this is going to be important mnemonic. What do we care about the area? Because the area again represents a probability of the chance of some event occurring. And you might say, well, okay, and so again, this is how we are going to determine if an event, a summary, a data value are outliers or common, for example. And again, why do we care about that? Because when it comes to making decisions with using statistics, we're often asked some question, like for example, does this drug work? And the answer to the question, does the drug work, relies on if the result is so unusual, if we assume the drug does not work. Okay, and we'll talk about this more later in the course. But we want to calculate the area because it tells us something about our measurements, how likely they are or unlikely they are, and then using that we make a decision. Okay, so the areas that I'm about to describe to you are not exact; they are approximations. And yes, you want to memorize these. Um, and and again, this is just about to make everything just easier to recall. And the reason you want to memorize is just the same reason you memorize your multiplication table. Okay, it would be terrible if if I asked, what's 4 times 3, and you had to reach for a calculator. In other words, if you're going to go 4 times 3, yes, you can memorize it, but after a while, you also get to know what it actually represents. And this is going to be something similar. So often this is called the 68, 95, 99.7 rule, or sometimes you'll see it called the empirical rule. And again, empirical means you actually test this out by gathering lots of samples, and then you make a determination as to what is actually occurring. So what is it I want you to remember? So I'm going to draw three curves here. A lot of times books will write them only one curve and mark this up, but I want to separate it so you're clear as to what this means, because I've seen this done in books, and all of a sudden, students, what we think is pretty darn clear, what we're trying to communicate, it turns out the student has other things in mind as to what we just drew. So right now, what we're after is, what is the area? How often will you get a value, a data value that is between -1 and 1 standard deviations? And again, the way we're going to represent this is the following. So notice my z-score is my measurement at the moment. And what's the chance that it's between -1 and 1? Also, just for your information, I'm not gonna beat this to death, but because it's continuous, equality or inequality will make a difference here. And why is that? Okay, I'm gonna just make this one thing known to you. If I ask you, what's the chance that you will get a z-score equal to 1, exactly equal to 1? Well, the answer to this question is 0. And you start going, so there's no way I can get a z-score equal to 1? Is that what you're telling me? And the answer is no. You can get a z-score to be 1. But what this is saying is that we cannot predict single values. And why is that? Why cannot predict single values from here? Because think of this as a continuous, and here, this will make the idea of continuous a little better known. Let's say that I have a 6-sided die. Okay, just a normal 6-sided die and so on. And I ask you, look, what's the chance that this die will land on 2? And you realize, well, I mean, assuming this is a fair die and there's 6 sides, so there's 6 sides, but only one of them has the number 2 on it. So out of the 6 possible sides, only one has it, so it's 1/6. Okay? So you come to this determination, assuming everything's equally likely, but there's only one chance that you're going to get the 2 popping up out of 6 possible chances, and that's how we get that probability. Okay. Now, at the bottom is everything that can happen. Total things in the population. Okay, which is only 6 values. But when it comes to this curve, how many things are in this population? How many things are possible? And the answer is the number of items is infinite. And now what I'm asking is, what's the chance of getting a 1, exactly a 1, out of infinite possibilities? Well, I would draw this, but this doesn't make any sense. The answer would not be, so for example, if I ask what's z equals 1, 1 over infinity doesn't make any sense. Infinity is not even a number. It's just an idea. So this is not even a calculation. But what does happen is this: as the population, if we're only after one thing, right? So if you had calculus, this might make sense. If and I'm going to just call n for population here. As my population goes up, and if I'm only after one thing, I'm going to say I'm after one thing, then this approaches 0. Okay, so again, if you try this, make 1 over n and just start making n bigger and bigger and bigger, what happens? Well, this whole thing is approaching 0. So really what we're going to say is the same thing. If you just have one thing and n possibilities, we'll just define the answer to be 0. It doesn't mean that it cannot happen. The better way to think about it is that we cannot predict it occurring. Okay, so we just define it as a 0. So now the question is, what is the chance between -1 and 1, including -1, or not including? It wouldn't matter, because the single number is meaningless. And the answer is 0.68. In other words, that number right there. So there's a 68% chance you're going to get a number between -1 and 1 standard deviations. Okay. So yeah, I think you might see where this might be going if I then go 2 standard deviations. So go here, here, 2, here, here, -2. What's the chance that I'm going to land between these two numbers? Okay, the area above tells you the answer, and the answer here is going to be 0.95. Exactly. So really, the question here is, what's the chance that I am now between -2 and 2? Let me just draw equal, and the answer is 0.95. Just like the answer here was 0 here, 0.68. Okay, so let's do one more here. So question again, what is the probability? So I'm gonna just take some, to speed this up a little bit. If I go -3 to 3, what is this area? So you can see that it's almost nearly all of it, but it's not quite all of it. Again, you cannot get, no matter what, if I went -4 to 4, I wouldn't get all of it because I can't. This curve never touches, but it's so close to all of it that I might as well be all of it, but it's not. So again, what's the chance of getting a value between -3 and 3? The answer is 0.997. Again, nearly 100%. Okay, but I can never get 100%. I can just keep going and adding more nines there, but I can never get the number 1 to appear. Okay, so definitely what you want to do is memorize these three. Memorize, please. And again, what this here means is, okay, what the statement, for example, is saying in words is the chance is between -1 and 1 standard deviations from the mean is, again, approximately 68%. Okay, and that is the meaning of that. So now let's use this to do the following calculation. Using the 68.95% rule, find the following value. The probability that my z-score is going to be greater than -1. So what you want to do, and you want to do this every single time. First, you draw a picture, and sometimes students just refuse to do this, but I use it all the time. Or they say, I don't know how to do this, but then refuse to draw this picture. So I'm going to draw it because what is it going to do for me? It's going to orient me. Okay, it gives me orientation. So having memorized this, I'm going to draw from memory what it is that this represents. So now I'm after z being greater than -1. So I know that it involves -1 standard deviation. So notice I'm going to draw this one, the 68, because it involves the -1 and 1. I'm not going to draw 95, or I'm not going to draw 99.7 because this doesn't involve them. So, and that's the reason I separated these into 3 different graphs. So you're not tempted to try to draw the whole thing, which is useless. So I'm going to draw my z here and label my axis. And then here's what I'm going to do next. I'm going to, maybe underneath somewhere, so that it's clear, I want to describe what I'm after. I'm after z being greater than -1. Again, it doesn't include that -1 right there. But again, as I mentioned, it doesn't really matter equality here. is useless as far as calculation purposes. So that's what I'm after. Okay. All right. But what do I have? I have this knowledge that this is 68%. And now I realize that what I'm after, again, it's good to kind of even highlight this. I'm going to maybe draw a little marks here. Is this area plus this area. So it's going to be 0.68 plus whatever this area is. So the question is, what is that area? And now here's where knowing facts and statistics is important. So one thing that you want to memorize is this. Uh, the area under a normal curve is 1 square unit, the entire thing. Okay, so how does that help us? Well, since what I want is all, I know this part, but I need to know what this area is. So it would be helpful to, well, figure what this is. However, what do I know? This tail and this tail together, what are they? How much is that? Well, the entire area is 1 or 100%. So if I subtract 1 minus 0.68, it gives me what is left over, which is 0.32. So the sum of this area plus this area is 32%, but I only want half. So since I only want half, I'll cut this in half, give me 0.16. So it turns out that this area here is 0.16. Okay. So one way to think about this is, so what is the area greater than 1? Well, it's going to be 0.68 plus this 0.16. And that gives me what? So I got what, 78 plus 4, it's 84, 0.84. So this is the probability of getting a z-score greater than -1. Okay, so I grab a number at random, and that's the chance of that happening. Okay, but note, I had to draw my picture, I mark what I want, and then slowly doing the little calculations, I come over here. And notice the way I'm writing this, I do my first calculation, take the result of that, come over here, do my next calculation. You know, I keep each one of these separate, and I'm expecting you to do the same thing. And then I'm going to write what I'm after, and then equal to, and how I'm getting my answer. So this right here, this work, if I was the reader, I can go back and figure out where all these numbers. If you don't do this and you start writing this, you're leaving the reader blank, right? And then, of course, you add these two numbers, and I'm assuming that gives me the 0.84. All right, so let's try another one. Using the 68, 95, 99.7 rule to find the following. -1, excuse me, -1 is z-score from -1 all the way to 2. So again, I'm going to draw a picture. I'll draw my normal curve. I'm going to put my 0 again, notice right smack in the middle. And now I'm going to notice something. It does involve two things. It involves, again, -1 before. Now it involves 2. So I'm going to come over here and draw -1. And then I'm going to come over here and draw number 2. Now, really, the area I'm after is between here and here. Okay. So now I'm going to just mentally break this up. Like I could do this, like I did here, and then find the area between 1 and 2, right? Like sort of like I did here. But I'm not going to do that. And why not? Because I'm thinking of an easier strategy. And what is that easier strategy? Well, that's the one. 68%. 68% is from here to here, right? And it'll be easy to write that down. But what about the other one? The 95% would be, in fact, I'm going to come over here and write that one in. It will be from here to here. Why not I do this? Instead of trying to use the full values here, why don't I think of breaking this problem up into two parts? The middle from here to here, and then from here to here. So in other words, what I'm about to do is, why not just do the following calculation? Calculate from -1 all the way to 0. So notice how I'm using this. I'm just trying to express what I'm after. And then I'm going to go from 0 to 2. That's what we're about to do. And you go, well, how's that going to work? Well, again, from between -1 and 1, it is 68%. But if I go from -1 to 0, that's only half of this value. So this is half of that value, half of the 68. What about here? Well, from -2 to 2 is 95, but from 0 to 2, it's 95 divided by 2. So really what I have now is between -1 and 0 is half of that area, plus this one is going to be half of the 95%. Okay, so when I do this, I get 0.34 plus 0.475, add them together, and I get 0.815. Okay. All right, we'll do one more here. Using the 68, 95, 99.7 rule, find z greater than 2. So I'm going to do that. I'm going to draw my picture. Then I'm going to draw what I'm after. What I'm after is 2 and greater. And again, since now it only involves 2, I'm going to just come over here and do this. Just to remind myself that the area between -2 and 2 is 95%. Okay, but now I also, what am I after? I'm just after this little part right here. Nothing more. So why not do what I did in the first one? In the first one, I figured out what this little tail is. And then, of course, added it to the other part because I wanted that. But here, I don't need to do that. All I'm after is the tail part. I don't care about the middle part at all. But I can use exactly the same strategy. So the strategy is subtract from 1. That gives me 0.05. And then take that result, divided by 2. I get 0.025. So really, what I have here is, if I put both of these ideas together, z being greater than 2 is going to be 1 minus 0.95, and then take the result and divide it by 2. And that gives me 0.025. Okay. So again, notice I found these answers, but using only this fact. And we want to do this so just we get familiar. Really what we want to remember is, and we're forcing you to remember that between -1 and 1 is 68, between -2 and 2 is 95, and between -3 and 3 is 99.7.